let's take a look at the activity of radioactive decay now. Activity is the actual number of decaying nuclei per second. In other words, it is this rate, delta n over delta t, right? That's a rate, right? Is going to equal to negative lambda over times n. This lambda is not wavelength. It's called the decay constant, and we're going to talk more about that in a bit, but just know so far that this is this thing called a decay constant. Okay? Now, one of the first things that you should know about this formula is that it's a little bit tricky because we have n on this side and n on this side. In other words, the rate at which something decays depends on how much you already have, right? So if n is the number of nuclei that you already have, right, the decay rate must depend on the number of nuclei, because the more nuclei you have, the larger the rate at which it's going to decay. So integrating this requires a little bit of calculus, and I'm not going to make you do it, but I do just want to let you know a couple things. One is that the units of activity, so this is activity, right? Activity is the number of nuclei per unit time, or really dn dt. And the units of this are this weird word called becquerel. Becquerel. You can see it there, and there's like a little BQ for the notation of it. Okay, so now what happens if you do integrate this equation? Okay, what happens if you integrate both sides of this? Well, you get a formula that will tell you the number of undecayed atoms left if you start out with N0 nuclei to begin with. Okay, so let's say that we integrate this, we have this many nuclei left, or undecayed atoms, equaling the number that we started with, N0, and naught, times e to the minus lambda t. And remember, lambda is the decay constant, and one way to think about the decay constant is that it is equal to ln of 2 divided by the half-life. Okay, so another way to rewrite this equation would simply be the number of undecayed nuclei equals the original number of nuclei, e to the minus ln of 2 times t over the half-life. Okay? This is a super powerful equation, and this is ultimately what allows us to be able to date ancient objects, right? Because we know that for a given t, we can know how many undecayed nuclei there are left, right? So in other words, if we know the rate at which something's decaying, right? Or we know how many undecayed nuclei we have left compared to the original sample, we can easily solve for t, the amount of time it had to have been decaying, and that t is the age of the thing, right? So this becomes very, very powerful tool in biomedicine, archaeology, all that. Okay, so let's take a little look at how we might use this equation, all right? So suppose that you have 3 times 10 to the 7 radon atoms trapped in a basement. And this is a legitimate concern. This is a thing that you may have kind of seen in the news, which is radon in basement. So suppose that you have that many radon atoms trapped in a basement at the time the basement is sealed against further entry of the gas. The half-life of radon is 3.83 days. How many radon atoms are left after 31 days? Okay, well, I'm going to give you a guess. You are going to use the same equation that we just learned, right? That is that the number of atoms left in any sample equals the original number that we started with, e to the minus lambda t, right? So what do we know here? We know that the half-life of radon is 3.83 days. That tells us we can easily find our decay constant lambda. So lambda, remember, is just ln of 2 over the half-life, right? So that's ln of 2. hopefully know how to put that in your calculator. It's 3.83 days. Make sure you're being consistent with your units, so that's days, right? That means that lambda is going to be 0.18 days to the negative 1. Okay, so now we can just go ahead and put this in here. We have n equals, remember, we originally started with 3 times 10 to the 7 atoms of radon, so 3 times 10 to the 7 atoms, okay? E to the minus, we just found it, people. I'm not trying to be crazy. I'm not trying to be crazy. Minus 0.18 days times T, which is how long we're looking at, right? That this radon's been contained, and that's 31 days. So remember, these units have to be the same. So if we're putting in T in terms of days, then lambda has to be inverse days, okay? If T is years, lambda has to be inverse years, okay? So we put that in our calculator, and we find out that there are going to be about sorry, this shouldn't be negative 7, it's plus 7. So there's still going to be 1.13 times 10 to the 5 atoms of radon after a month of sealing it. All right, not super promising. That's still quite a bit of atoms. So you can see why, you know, this could be a potential health concern. This whole issue of how radon enters a house. And by the way, if you want to look this up, there's the picture here kind of demonstrates that process, but it's kind of interesting. I'm not going to get into it here, but search it if you want to. That is all I have to say for that. So I'll see you in the next video when we talk more about how to date ancient bodies like the one that the German tourists found in the Alps.